Imagine sitting in a quiet room, peering through a window that looks out across the entire history of the universe. For years, all you see is the standard flickering of stars and the predictable hum of the cosmos. But then, it happens. A flash so bright and so brief that if you blinked, you would have missed it forever. NASA's most sensitive instruments have just captured a signal that traveled through the void for over 3 billion years. It didn't come from a star, it didn't come from a black hole, and it doesn't match any known pattern of celestial mechanics. This isn't just a faint whisper. It is a scream across the light years that has left the world's leading astrophysicists scrambling for answers. We are talking about a discovery that challenges our understanding of physics, the limits of energy, and the possibility of what might be lurking in the far reaches of the deep dark. This is the story of a signal from 3 billion light-years away that nobody can explain, and the truth might be stranger than anything we have ever dared to imagine. To understand why this signal is causing such a massive stir in the scientific community, we first have to talk about the scale of the universe. When we say something is 3 billion light-years away, we aren't just talking about a distance that would take a rocket ship trillions of years to reach. We are talking about looking back in time. The signal NASA detected has been traveling at the speed of light for 3 billion years. When that burst of energy first began its journey, Earth didn't even have complex life. Multicellular organisms hadn't even appeared yet. For that signal to reach us today, after crossing such a vast, expanding ocean of empty space, the source must have been unimaginably powerful. We are talking about a release of energy in a fraction of a second that is equivalent to what our sun will produce over its entire 10 billion-year lifespan. This brings us to the phenomenon known as fast radio bursts, or FRBs. These are mysterious pulses of radio waves that last only a few milliseconds. Since they were first discovered in 2007, they have become the greatest mystery in modern astronomy. At first, scientists thought they were one-off events, perhaps the result of two stars colliding. The new signal from 3 billion light-years away is different. It is what scientists call a repeater. It isn't just a single burst, it's a rhythmic, repeating pattern. And it isn't coming from just any part of the sky. It is coming from a very specific, very crowded environment that suggests something truly bizarre is happening at the source. When NASA used its deep space network and coordinated with powerful ground-based telescopes like the CHIME array in Canada, they found that this specific signal, dubbed FRB 2019-0520b, is sitting inside a dense cloud of magnetized plasma. This is a very noisy neighborhood. For a signal to stay clear and coherent through all that interference for 3 billion years is a mathematical miracle. It's like hearing a clear, ringing bell in the middle of a hurricane from 5 miles away. Whatever is creating this signal has to be so intense that it can punch through layers of cosmic debris and magnetic fields without being distorted. So, what could it be? The first and most popular theory among astrophysicists is the magnetar. A magnetar is a type of neutron star with a magnetic field so powerful it would dissolve your atoms if you got within 1,000 miles of it. These are the remnants of massive stars that have collapsed under their own weight. Sometimes, these stars undergo what we call a starquake. The crust of the star cracks, releasing a monumental amount of raw energy. This could explain the power of the FRB, but it doesn't quite explain the perfect repetition and the specific frequency of the new signal. Magnetars are chaotic and violent. The signal NASA found is oddly precise. This precision is what has led some researchers to explore more exotic possibilities. Could the signal be the result of a highly advanced alien civilization? Before you dismiss that as science fiction, remember that some of the most respected names in physics have considered it. If you were an intergalactic species trying to move massive spacecraft at nearly the speed of light, you might use a powerful beam of energy to push a light sail. As that beam sweeps across the universe, it would look exactly like a fast radio burst to a distant observer. The fact that the signal is repeating and comes from such a distance could mean we are witnessing the energy leakage from a transport network that spans galaxies. While NASA officially looks for natural explanations, the mathematical signatures of these bursts continue to defy the models of how stars are supposed to behave. But let's look at another possibility that is just as mind-bending. Black hole interaction. Somewhere 3 billion light-years away, a magnetar might be orbiting a supermassive black hole. As the star swings around the black hole, the intense gravitational pulling and the interaction of their magnetic fields could create a lighthouse effect. Every time the star reaches a specific point in its orbit, it sends a burst of energy toward Earth. This would explain the repetition and the massive energy levels. However, if this is the case, It means we have discovered a cosmic engine of such intensity that it bends the very laws of physics we have developed here in our quiet little corner of the Milky Way. The problem with the black hole theory is that the signal doesn't show the typical stretching we expect when light is caught in a massive gravitational field. It remains sharp. This has led scientists to look at something even more rare, a boson star. These are hypothetical objects made not of atoms, but of dark matter particles called bosons. If they exist, they would be invisible and extremely dense. A collision involving a boson star could create a signal that looks like an FRB but behaves in ways that traditional neutron stars cannot. The discovery of this signal might be the first time we are seeing evidence of dark matter actually interacting with the visible world in a tangible way. Think about the sheer number of these bursts. Scientists estimate that there are 1,000 fast radio bursts happening in our sky every single day. We just don't see most of them because we aren't looking at the right spot at the right time. But this repeating signal from 3 billion light-years away is like a persistent neon sign in the dark. It is demanding to be understood. If we can figure out what is creating it, we unlock a map of the universe's structure. You see, as these radio waves travel through space, they pass through clouds of electrons. By measuring how the signal is delayed and dispersed, we can actually weigh the empty space between galaxies. We can find the missing matter that has eluded us for decades. This signal is essentially a probe, sent by nature, to tell us where everything in the universe is hidden. But to use it as a tool, we have to know what the source is. If we don't know the starting point, we can't accurately measure the journey. NASA's current mission is to pinpoint the exact galaxy where this burst originated. When they find it, they will look for other signatures, gamma rays, X-rays, or gravitational waves. If the source only emits radio waves and nothing else, it becomes even more terrifying. A natural object that only produces radio pulses at that energy level is almost impossible to explain with our current understanding of how matter behaves under pressure. There is also the plasma lens theory. Imagine a normal, relatively weak radio source that just happens to be perfectly aligned with a massive cloud of gas. That gas cloud could act like a giant cosmic magnifying glass, focusing the signal and making it appear millions of times stronger than it actually is. This would mean the source isn't an impossible monster, but just a normal star in a very lucky position. But for that alignment to last for years through the motion of stars and galaxies is statistically very unlikely. It would be like a sniper hitting a bullseye on a moving train from 1,000 miles away, over and over again. Every time we get a new data packet from this signal, it adds a new layer of complexity. Some researchers have noticed that the pulse has a certain chirp to it. The frequency changes as the pulse happens. This is often a sign of a rotating object, but the speed of the rotation would have to be so fast that the star would technically be on the verge of flying apart. We are pushing the limits of structural integrity for solid matter. If it is a star, it is a star that is doing something it shouldn't be able to do. Let's talk about the human element of this discovery. Imagine being the astronomer who first sees the spike on the monitor. You check for glitches. You check if someone was using a microwave in the break room. Yes, that actually happened once in Australia where a signal from space turned out to be a microwave door being opened too early. But this signal has been verified by the Green Bank Telescope, the Arecibo Observatory before it was lost, and the global network of radio dishes. It is real, it is out there, and it is coming for us. Not in a dangerous way, but as a challenge to our intellect. It is a reminder that the universe is far more active and far more energetic than our textbooks suggest. We live on a planet where we struggle to generate enough energy to power a city. Out there, 3 billion light-years away, something is flicking a switch and releasing enough power to light up the entire observable universe for a millisecond. It makes our greatest achievements look like a flickering match in a thunderstorm. This humility is the core of astronomy. The more we learn about these signals, the more we realize how little we know about the high-energy universe. Is it possible that these signals are the result of cosmic strings? These are theoretical cracks in the fabric of space-time that formed shortly after the Big Bang. They are thinner than an atom but would have the mass of an entire mountain range per inch if two cosmic strings were to cross, or if a loop of a string were to snap. It would release a burst of radio energy that could travel across the age of the universe. If FRBs are the sound of the universe's fabric snapping, then we aren't just looking at stars. We are looking at the fundamental architecture of reality. The signal NASA detected also has a strange memory effect. Every time it repeats, it seems to carry a bit of the previous burst's signature. This implies that the environment around the source is being physically altered by each pulse. The radiation is so intense that it is essentially clearing out the gas and dust around it, creating a tunnel of empty space through which the next pulse can travel more easily. This self-clearing mechanism would be a brand new discovery in astrophysics. It shows that these events aren't just passive flashes. They are active architects of their own local space. Consider the binary neutron star model. Two of these ultra-dense objects spiraling toward each other, their magnetic fields intertwining like two giant magnets. In the months before they finally merge, they would create a series of repeating, intensifying pulses. If this is what we are seeing, then we are witnessing a countdown. We are watching a 3 billion-year-old recording of a cosmic collision that has already happened. By the time we see the final massive burst, the stars themselves will have been gone for eons, turned into a single black hole. We are watching the ghost of a star system scream as it's being erased. The scientific community is currently in a global campaign. Every major radio telescope on the planet is taking turns staring at this one spot in the sky. They are trying to catch the burst in real time with other instruments. If we could see a flash of light at the same time as the radio burst, we could confirm the visible light signature of a magnetar. But so far, nothing. The bursts are invisible to our eyes, invisible to X-ray telescopes, and invisible to gamma-ray detectors. This ICA radio-only nature is the biggest clue and the biggest frustration. Most high-energy events in space create a mess across the whole spectrum. But this signal is clean, it's focused, it's professional. This focus is what keeps the advanced technology theory alive in the back of everyone's minds. A natural explosion is usually messy. It scatters energy in every direction and across every frequency. But a purposeful signal, or a beam used for propulsion, would be narrow and efficient. While scientists are trained to look for every possible natural explanation first, the efficiency of these bursts is something that hasn't been fully explained by any star model. We are searching for a needle in a haystack, and the needle seems to be made of a material we haven't discovered yet. There's also the question of redshift. As light travels through the expanding universe, its wavelength stretches out, moving from blue toward red. Because this signal is so far away, it has been stretched significantly. This means the original signal at the source was even higher in frequency than what we are detecting. It was likely in the terahertz range, hovering between radio and infrared. This moves the energy requirements even higher. We are talking about the extreme of the extreme. As we look deeper into the data, researchers are finding that these bursts might not be as fast as we thought. Some of them have substructures, tiny micropulses within the millisecond-long burst. These micropulses are only nanoseconds long. This tells us the size of the source. Basic physics says that an object cannot change its brightness faster than the time it takes light to cross it. If a signal is nanoseconds long, the source must be only a few meters across. Imagine that. An object the size of a small car, 3 billion light-years away, generating enough energy to be seen across the entire universe. That is not a star. That is something else entirely. It is a point source of energy that defies everything we know about how much power you can pack into a small space. This small source problem is the current wall that researchers are hitting. Even a neutron star is 10 miles wide. A black hole is miles wide. To have a source that is only meters wide suggests we are looking at a coherent process, like a laser, rather than an explosion. A relativistic beam of particles could create this. But what is accelerating the particles to such speeds without tearing the whole system apart? The physics required to maintain that kind of stability is beyond our current laboratory capabilities to test. NASA's next step is integrating the James Webb Space Telescope with the radio observations. While Webb looks at infrared, it might see the heat signature of the galaxy hosting the burst. If the galaxy is a Tor-burst galaxy, one that is making new stars at a frantic pace, then maybe the signal is just a normal part of a star's birth and quick demise. But if the galaxy is old, quiet, and stable, then there's no reason for a magnetar to be there. An old galaxy with an impossible signal is a much bigger mystery than a young, chaotic one. We also have to consider the cosmic distance ladder. If our measurements of how far away these things are even slightly wrong, the whole energy calculation changes. But the redshift data is very solid. We know they are far, We know they are moving away from us with the expansion of the universe. This means we are forced to accept the energy levels. We are forced to accept that there is something out there in the dark that is far more capable and far more energetic than we are. As we continue to listen to this signal, the explanation might not come from a telescope at all. It might come from a physicist at a whiteboard who realizes that our understanding of how magnetic fields interact with gravity is incomplete. We are at the same stage with FRBs that we were with quasars in the 1960s. At the time, quasars were impossible objects that produced too much energy for their size. It took us decades to realize we were looking at supermassive black holes feeding on gas. FRBs are our century's quasars. They are the new frontier of the impossible. What if the signal is a ping from the early universe? There are theories about primordial black holes that formed in the first few seconds after the Big Bang. These would be tiny, the size of an atom, but with the mass of a planet. As they slowly evaporate over billions of years, they might release bursts of energy. If we are detecting the final moments of these ancient objects, we are literally watching the leftovers of the creation of the universe disappear. This would give us a direct link to the first moments of time itself. Whatever the answer turns out to be, the journey of discovering it is revealing more about our universe than we ever thought possible. We are learning about the hidden matter in the void, the intensity of magnetic fields, and the limits of space-time. This signal from 3 billion light-years away is a gift. It is a puzzle that is forcing us to become a smarter species to solve it. NASA hasn't just detected a noise, they have detected a question, and the answer to that question will likely redefine our place in the cosmos. We should keep looking up, and we should keep listening. The universe is not a quiet place. It is a roaring, flashing, energetic masterpiece, and we are finally developing the ears to hear it. The next time you look at a patch of empty sky, remember that in just the last few seconds, dozens of fast radio bursts have passed right through you, carrying news from billions of years ago. Most of them will never be explained, but this one repeating signal is our best chance to finally uncover the secrets of the deep dark. The explanation is out there, moving at the speed of light, waiting for us to catch up. The mystery of FRB 2019-0520b is a reminder that we are still in the early days of space exploration. We think we have the universe figured out, and then a millisecond of radio waves from across the void tells us how wrong we are. It's an exciting time to be alive. A time when the impossible is detected on our monitors every day. The signal is still repeating, the telescopes are still watching, and the math is still being written. The universe is calling, and we are finally beginning to understand the language. Stay curious, stay humble, and keep looking toward the stars, because the next signal might be the one that changes everything forever. The signal is out there, it's loud, it's strange, and it isn't going away until we find out exactly what is happening 3 billion light-years from home.